Hello everyone, my name is Bosio and I'm a junior in high school. I'm excited to tell you about my research project regarding membrane-based, solar-driven greywater filtration. My project spanned over 1,000 hours of design, experimentation, and analysis. Essentially, my work addresses the water-energy nexus, a feedback loop in which water is required to produce, transport, and cool energy, while energy is required to extract, treat, and distribute water. This cycle contributes to climate change and water scarcity worldwide, making efficient water reuse a critical challenge. I first became fascinated by sustainable research at the World Sustainability Summit in Hungary, where hundreds of representatives from global industries presented their latest innovations regarding climate protection. After talking with as many attendees as I could, I began to understand how careful material selection and efficient energy systems can produce compounded benefits across sectors. That experience, along with internships at sustainable chemical and agricultural companies, volunteering on environmental projects within my community, and family snorkeling trips that fostered a respect for aquatic environments, guided me towards water treatment research. Then I met my research mentor, Dr. Lipscomb, and was introduced to membrane water filtration. I realized that greywater, water from household sinks, showers, bathtubs, and washing machines, offered a relatively simple water matrix for treatment. Unlike sewage, it's easier to purify, yet its potential remains largely untapped in industrial applications. My goal became clear: to design a system capable of efficiently recycling greywater while minimizing energy inputs. Building creatively on the basic design of a solar still, my system incorporated a membrane, an air gap, and condensation surface piping to optimize thermal gradients across the system. Membrane distillation is guided by temperature-dependent vapor pressure differences, and to enhance this process, I incorporated two distinct surface modifications on standard PTFE membrane. The first, a carbon cloth placed directly above a PTFE membrane to enhance the concentration of thermal energy at the membrane interface. And second, a conformal coating of carbon black was applied directly to PTFE to increase contact area and improve heat transfer. With the guidance of Dr. Lipscomb, I incorporated an air gap, which helped to insulate the interface and strengthen thermal gradients. In preliminary experiments, permeate accumulation was relatively low. I traced this to an insufficient temperature stratification between the air gap and the condensation surface. To address this issue, I established an ice bath system, which circulated cool air across the condensation surface. Water droplets visibly formed, and permeate accumulation more than tripled. Testing sequential water types revealed important trends. Saltwater yielded the lowest permeate accumulation, likely due to electrostatic attraction, which makes separation much harder. But the most promising results came from carbon black composite membranes, which achieved an energy intensity of 1.01 kilowatts hour per liter. If this membrane was scaled to a 1 meter squared active area, operating continuously under 24 hours with 320 watts per meter squared irradiance, then the system could yield approximately 31.2 liters per day, which adds up to 11,388 liters per year. A single, modular system smaller than the size of a residential solar panel could offset a person's daily non-potable water demand by 8 to 10%, if active airflow was replaced by passive, convection-driven currents. Looking forward, I'm excited to expand my research with hierarchical material and desiccant layering, hopefully reducing energy requirements and improving extraction efficiency. Honestly, this project has challenged me technically and personally, but I'm incredibly proud of the progress and the knowledge I've gained. I'm deeply grateful for the incredible community who's helped me through my research process and Davidson Fellowship application journey. Graduate student Hamed Ranema, who let me come early and stay late, even on Christmas. Parisa Safari and Dunanji, who taught me about the family behind every research project. And finally, Dr. Glenn Lipscomb, with whom none of this would be possible. His curiosity and guidance has propelled me further than I ever imagined. Thank you. I also want to express my heartfelt gratitude to the Davidson community. Thank you for watching my video, engaging with my project, and providing me the extraordinary opportunity to propel my research forward into the world. I hope that my work not only advances sustainable water treatment technologies, but demonstrates that innovative solutions at the intersection of water and energy can help build a more efficient and resilient future. Thank you.